Hi everyone, I'm Alibaba from the SesamX finite element software. Today in this video I'm going to show you how to create a simple shell finite element model using the Salome preprocessor and how to run a simple linear static resolution using the SesamX solver. This video tutorial is divided into three parts. The first part is about the creation of the geometry and how we can build the mesh with Salome. The second part will deal with the mesh export from Salome to SesamX and how we can run the SesamX computation. And the last part is about importing back the results from SesamX to Salome in order to visualize the mesh deformation. But first, let me introduce SesamX briefly. SesamX is a brand new finite element software. I invite you to check our website that I have on my background and also our blog, in which you can find very specific articles about what's implemented inside SesamX. For instance, we have great articles about shell formulation that we're dealing in this tutorial. I think we are done with the introduction. Together, let's open this tutorial. For this tutorial, I've decided to create a geometry from the drawing you are seeing on your screen. If you are interested, you can find in the description below the video a link to this image so that you can try it on your own. The key point to keep in mind is that this drawing describes the 3D representation of our part. But in the case of our tutorial, we aim at modelizing a 2D shell finite element model. So basically, we need to extract the mid-surface of this 3D representation. And that's the model I've created using Salome. I'm now in Salome. As you can see, I'm in the shaper module here. So basically I've created the whole geometry in this shaper module. In this video I will not dive too much on how I've created this geometry using Salome. If you are looking for this information, I invite you to check the Salome website for the documentation and also for that great tutorial. I want you to have a look here at the geometry I've created. In fact, you can see these are only 2D shell surface with no thickness. On the left part of my screen, I've just unfolded the tree structure containing all the features that are used to build this geometry. I want you to know that I'm not a CAD expert and I think there are better ways to build such a model. But in the case of our tutorial, I think this is enough. I have attached in the description below the video this model so that you can use it as the starting point of this tutorial and you can modify it as you like. I want you to pay attention to one particular folder here, the groups folder. So this group folder contains basically geometry groups that I have created. There are 5 of them. All of them are hidden, and for instance, I will show the first one. So when I hit this button, I can show the content of the whole one group. And as you can see on the screen, this group is made of the 2 inner circles, this one and this one. I can do the same with the whole 2 groups, and it's the same, and with the whole 3 groups. I've also created a top connection and a bottom connection groups. The top connection group is made of this line here, and the bottom connection group is made of this line. So these groups are important because they will be used as the building block of the finite element groups that we will be creating later on. So basically, we will be able to create a finite element groups called whole1 that will have nodes that rely on this line here. I think it's the best practice to create the groups at the geometry level because it makes it much easier to create finally the finite element groups. And I think that's all we need to know about this geometry right now. The last step is to export this geometry to the geom module by clicking this button. I'm just hiding the groups here so that we are not polluted with them afterwards. And I'm also hiding the whole part here. Then I go to the geometry module. If I unfold it here, I find here my partition and if I show it, I see my whole part. Underneath, I can find also the groups that I have created. That's pretty much with the geometry module. Then we just head to the mesh module. So where we are in the mesh module, by default the geometry is hidden. So first I will show it. As we've done before, I go into the tree and I click the visibility button here. Or I can right click on the part and hit show. For instance, I've hidden it and I can show it this way. And you see the part that appears on the screen. So the first thing we are doing now is to create a mesh. So basically here I have a mesh folder, and if I unfold it I have nothing underneath. So to create the mesh, I click on this button, so it's create mesh, and so I have a panel that appears and it asks me first for a name. So I will call it connector mesh. And I have to select a geometry here, so I click on my partition. And then I have 4 tabs here: 3D, 2D, 1D, and 0D. So these tabs relates to the kind of mesh I want to build. So you see when I've chosen the partition, the 3D tab turned gray. It's because, as we've seen previously, my geometry is only shells, so it does not have a 3D description, and I can choose among 2D, 1D, and 0D. So I have a 1D tab here because the way Salome build the mesh is first by meshing 1D element, and then from this element it derives the 2D mesh. So that's why we need to build first a 1D mesh and then a 2D mesh. But to make it simpler, we will stay in the 2D mesh tab here, because as we are going to see in a minute, we will have everything that we need. So if I go under algorithm here, I can choose basically the algorithm that I want to apply to create my mesh. And for this tutorial, I will choose the NetGen 1D 2D algorithm. So this one is very interesting here because it will build the 1D elements and the 2D elements without having to go to the 1D tab here. So I'm choosing this one. Then I have to select some hypothesis about basically the element's length, and by default I have nothing here, so I have to click on this icon here, and I have the choice here. I can choose the NetGen 2D parameters, so I will click on this to show it to show to you what appears. So I have a panel here with a lot of parameters that I can choose to control how the mesh is created. So you have very specific parameters, and I will not deal with them in this tutorial. Instead, I will use the NetGen 2D simple parameters because it makes it very easy to build a mesh. So as I have said before, first I have to select, I have to define the parameters for the 1D element. So I will check local length here because I prefer to define my mesh by specifying a length. For instance, I select 0.8. And for the 2D elements, I will just let this box checked so that I ensure that my 2D elements have the same size of the 1D elements. So this way I have a very uniform mesh. And I make sure to check the quad dominated box here. So it's important when you're doing finite element to check this box here, because it ensures that you have the most quad possible in your mesh. It's important because when, for instance, you are dealing with shell, quad shells elements behave way better than triangular shell elements. So in SesamX, for instance, our quad shell element is the MITC 4+, and it's a very good element, and our triangular shell element is the MITC 3+. It's also a good element, but the MITC 4+ is even better. So that's why it's important to ensure that you check this box. And it's a general rule among finite elements. If you take, for instance, other solver like Nastron, Abacus, you're way better when you stay with squad elements. So that's why we are choosing them here. And I click OK. Then I hit apply and close. And as you can see, while I was selecting my parameters, I have new nodes that appeared on my tree. So basically, so this one is about the parameters that I have selected, and this one about the algorithm that I have selected. I can see my mesh here, and there is a little panel that's saying that it's probably not up to date because I have defined my parameters, but I have not already computed my mesh. So that's why I'm going to do. I right click on my mesh here, and I click on the compute icon here. Then it computes my mesh. Okay, the mesh computation succeeded. I can see on this panel everything that was created by the basically the meshing algorithm. So I have no 0D elements. I have no balls element. I have 1D elements, as I said before, and I have also faces, so 2D elements, triangles and quadrangles. And as you can see, I have way more quadrangles than triangles. For our tutorial, because it's a shell tutorial, we do not need the 1D element. So we will see in a minute how to delete them. I can hit close. And as you can see, I have my mesh on my background. So I will hide the geometry here so that we see only the mesh. And I can basically see my mesh. So the next step is about adding the groups on my mesh. So first, I'm going to define a group that contains all the 1D elements that are in my mesh in order to remove them. And then I will define the groups that we have prepared in our geometry. So to create a group, I simply right-click on the mesh, on my connector mesh, and I select the create group here. So this way I can create my group of edges, of all the edges in my mesh. So I can select edges here. I have to provide it a name for this group, but I stay with the group one because, as you will see, we will no longer need this group afterwards. And I can select all, apply and close. Then here I have a group of edges that appeared. If I select it, you see that all my edges were selected. In order to remove the 1D element from my mesh, I will simply right-click on this group and select Delete Groups with Content. And it asks me for the groups. I hit Apply and Close. The group disappeared. And if I go back to my mesh, right-click on it, and I select Mesh Information, I have a very similar panel to the one that appears when we have completed the mesh creation. And now I can see that I have no 1D elements. So that's fine. Next, I'm about to create the nodes group that I have defined on the geometry. So basically the whole groups 1, 2, 3, and the connector line at the top here and the connector line at the bottom here. To do so, I right-click on the connector mesh and I select Create Groups from Geometry. I have to select either in elements or in nodes the groups, the geometric groups that I want to use to build my finite element groups. So for me, I will just use nodes group, so I will not choose the elements here, but I will choose the nodes. And I will select all my groups here so that I make sure that I create a node group for each of my geometry groups. I can then hit apply and close. And as you can see, I have my nodes groups that appeared here. I can visualize them by showing them. So for instance, the hole 1, you see now the nodes that appeared, hole 2, hole 3, the top and the bottom connection. In order to make SesamX run properly, I will also need a group that contains all my elements and all my nodes. So I will do the same as I have done with the 1D group. I select create group here, and my goal is to create a group that contains nodes and also elements. So in Salome, a group is either a group of nodes or a group of elements, but it cannot be both. In the opposite, in SesamX, a group can contain elements and nodes. In order to create a SesamX group that can contain at the same time nodes and elements, I need to create two groups in Salome with the same name, one for the nodes and one for the elements. And that's what I'm about to do here. So I will call this group all, so it's not very original. And first I will create the node group, so I check select all here, apply and close. Under the group of nodes I have a all group that appeared here, and I do the same for the element. I make sure to select face here and select whole. And I have my group of faces here. Both have the same name. So we are done with our mesh. We can now export it to the MET format. To do so, I right-click on the connector mesh here, and then I go to export. As you can see, there are multiple export formats that I can choose. Probably the best one is the MET file, and that's the one that is recognized by SesamX. So I will choose this one. And then I just have to select a location. Connector mesh, I'm fine with that. And I can hit save. Now if I go back to my file system, I can see that I have the MED file that appears here. This MED file is in fact an HDF5 file. So if you have an HDF editor on your computer, you can browse it and see what's inside. But we do not need it for this tutorial. The next step in our SesamX tutorial is to write the SesamX input file and run the SesamX computation. I've already prepared a SesamX input file, the connector input file.sx that I have here, and I'm going to edit it so that we can comment it together. Here you see the SesamX input file. You can recognize in brown here what we called functions. So each function is a call to SesamX and it asks it to perform an action. So we'll see what all of these are about. So the SesamX input file is basically made of different functions, one after the others. So I start from the beginning. The first function that we call is the useDatabase function. So this function tells SesamX where to store the SesamX database. So here we provide the relative path to the parent folder of the connector input file. Then is the createUnits function. You have to know that SesamX deals natively with units, and it defines default value for them. For instance, the default value for the physical quantity length is meter. In our case, we have to redefine the length unit because the MED file exported by Salome is in fact exported in millimeters. So I have to say that the nodes coordinate, which are of physical quantity lengths, are in fact millimeters and not meters. We'll see in the output file what are the units that are used by SesamX. If you wonder what are the units used, you just have to check the output file and you know for sure what was understood by SesamX. So to define this unit, I just give it a name here, so it's millimeter, and I give it the coefficient to the standard unit system. Next is the create model function. So this function just tell SesamX that we want to create a model named connector model and that it is of type finite element model, and if it's already existing in the database, then it has to override it. Then there is the create submesh function. So this function allows us to import the med file that we have exported in Salome. So we are telling SesamX that it has to import the connector mesh into the SesamX model here. Next is the create selection functions. This function is similar to the create submesh functions. It tells SesamX that we want to import the Salome groups from the connector mesh.met file into the SesamX connector model. Next is the create materials function. So these functions allow to define a material in our model. So here we define the material that is the AZ1020 in our connector model, and we give it the physical quantity, the Young modulus, the Poisson's ratio, and the density. Even though we do not need the density to perform a linear static resolution, we still have to provide it. Then we use the create properties function to tell SesamX which properties are attached to our elements. So here we want to apply a shell property on our elements, so it's the shell standard property. And we provided the shell thickness, 5 millimeters, the name of the material, and the elements on which this property applies. So here we are selecting the elements from the whole group that we have created in Salome. Then we define the boundary condition with the create constraint function. So with this function we are defining a boundary condition called bound case, and we are prescribing the displacement and rotation on the nodes from the whole one group. And we do the same for the nodes on the whole two group. So basically in our case here we are constraining the whole one and whole two, and then we will be applying a force on the whole three. And that's what the next function does, the create load function. So this function allows us to define a load on our model. So here we use the concentrated load, and we just say that we want to apply a force vector of 10 Newton along the x direction and no moment on each nodes from the whole three group. Then comes the solve linear static function. So this function tells SesamX that we want it to run a static linear resolution named linear analysis from the load case that we have defined previously and the bound case that we have also defined previously. And then comes the output image function. So this function tells SesamX that we want to output an image on our model. So here we want to output a displacement image composed of two fields, the translation field and the rotation field. So the translation field will be called the trans field, and the rotation field will be called rot field. And we want SesamX to compute this image from the solution lean analysis that we have computed just before. And we wanted to apply this output computation on the nodes from the whole group. So we have here our SesamX input file. Now I'm going to run it through SesamX. So I'm starting a new command prompt here, and I'm calling the SesamX program. So this path is the path to my SesamX dist folder. And to run SesamX, I will call the run sesamx.bat file, and I'm providing it the name of my input file, so this one. So I'm lazy here, I'm copy pasting. SesamX is running, you see that there are files that appeared here, and it's done. So, as you see, there are the .h file that appear, the .vtu file, and the .out file. The .h5 file is in fact the SesamX database that we have asked in the first function that we have put in the SesamX input file. Then the .vtu file is the image that we've asked SesamX to write at the end of the input file. And the .out file is the SesamX output file. So first thing when you've just completed the computation is to check the output file to see what basically SesamX has done. So I'm going to edit it to see what's inside. So this output file provides information about what SesamX have understood about what we have asked it to do, and then it provides additional information when appropriate. So for instance, SesamX understood that there was 11 functions to execute here, and that the input cards were properly formatted. As I told you when we were talking about the input file, there is a unit summary here, so that we can see that the length unit that we have defined, in fact, is correctly understood by SesamX, so it's in millimeters, and there is the right coefficient to the standard unit system. For instance, we use the thickness for our shell thickness, but we haven't provided it a unit for it. There is, if I go back to my create unit, we just have the create unit for the length. So this one is the default unit that we are seeing here, and the thickness, the default thickness unit is in millimeter. So that's why we didn't have to redefine it. And then for each function, basically SesamX tells us what it has done. The create submatch function, SesamX has properly imported the nodes and the elements. It's good to check this output file to see if there are warnings or errors during the computation. In our case, there is no errors and no warnings. Then the create materials function, the create properties function, the constraint, the load, the solve function. I have a listing of all the DOF, the degrees of freedom in my model, and the output image function that says that the image location is this one. So it's the one I've shown you previously in my folder. So that's it for the SesamX run. We can now import the .vtu file in Salome to visualize our mesh deformation. The last step of this tutorial is to import the image that we've created with SesamX into Salome. To do so, we go to the Paravis menu here. For those of you who are familiar with the Paraview software, you may recognize it here. In fact, the Paravis module of Salome is just a Paraview embedded into Salome. So basically, you will find all the Paraview functions available here. The first thing to do is to open the image into the Paravis module. So I go to the open icon here, and I select my image, the .vtu file. Then I have to hit apply. Now I can see my model in the visualization screen, and on the left panel I can see that Paravis understood that there are two fields in my image, the rotation field and the translation field. And for each of them I can see that there is also a unit beside the name. So the rotation field is in degrees and the translation field is in millimeter. These units is the output of SesamX. So it's SesamX who wrote them, and everything is consistent. The value that we are seeing for these fields are consistent with the units besides the name. So in order to see my model deformation, I have to apply a filter on my image. So I go to the filter menu here, alphabetical, and then I select the warp by vector. So this filter ask me first a field to choose. So in order to see something interesting, I will select the translation field, and then I can choose a scale factor. So I will choose something large so that we can see the deformation. And then I hit apply. So we can see here the mesh that has deformed. And I can also select here the translation field so that we see a map of the displacement magnitude. So for this tutorial, I basically have constrained the two holes, so this one, and I have applied force in the x direction here. So this is coherent with the boundary condition and the loading that we have applied on our model. So we are arriving at the end of this video tutorial. I apologize for my terrible English accent, and I hope you had a pleasant watching and that this video has brought value to you. If you have any comments or thought, you can share it in the comments below, or you can also contact us through our website. I try to put everything that we need for this tutorial in the description, and thank you for watching.